Okay, now we're going to get to the other type of problem that uses molarity, and that is a stoichiometry problem. Now, in contrast to dilution, dilution is when we are not running a chemical reaction. Dilution is just adding water to an existing solution to make it less concentrated and to increase the volume. In contrast, stoichiometry is when we are running a chemical reaction. And we solve stoichiometry problems by setting up dimensional analysis setups using conversion factors. And so if we're running a chemical reaction and we're going to set up a stoichiometry dimensional analysis, we can now use molarity as a conversion factor. And I mentioned this earlier. So just as we could calculate the stoichiometry when we were given moles, and we could calculate if we were given grams by converting to moles, we can also use molarity and volume to convert to moles. And notice again that molarity is a conversion factor. Which two units of measurement does molarity convert between? It converts between the moles of the solute and the liters of solution. It can interconvert back and forth between those two units. To show you a little bit graphically how we can set this up or how we can think about this, I'm going to draw out a scheme or diagram that kind of represents how we handle stoichiometry. So in the past, if you were given grams of substance A and you were asked for grams of substance B, that is a stoichiometry problem. And what we would do is we would go to convert to moles of A, and then convert to moles of B, and then convert out to grams of B. And to do the conversion from grams to moles and moles to grams, we would use our molar masses for those conversions. Remember, the mole to mole conversion is the heart of the stoichiometry. When you're doing a mole to mole conversion, that's the heart of the stoichiometry. Every stoichiometry has to go through a mole to mole conversion step because that is the only way that we can convert between two substances. Well, now we're going to expand that scheme a little bit more. If you are not given grams of a substance A, but you are given volume of a solution of A, you can still convert from volume to moles by using the molarity of the solution. And similarly, once you've done your mole to mole conversion, now that you have moles of this other substance B, you can convert to volume of a solution B by using the molarity of that solution. And so this is an expansion of our stoichiometry scheme by allowing us different ways to get into the heart and back out again of that problem. So here we go. We're going to use, as an example, an acid-base reaction. We're going to react hydrochloric acid with calcium hydroxide. And it's saying how many milliliters, what volume of that concentration of acid would be required to completely neutralize, that is to react with, that volume of that concentration of the base. Since it is a stoichiometry problem, we know that there is a chemical reaction taking place, and we know that we're going to go through the heart of the stoichiometry solution, and that is a mole to mole conversion. So we know that we're going to have a completed and balanced equation, and that's going to give us the molar ratios. So let's do that first. So step one, let's write our completed and balanced chemical equation. All right, so I've got hydrochloric acid reacting with calcium hydroxide. This is an acid-base reaction, so the hydrogen from the acid is going to pair up with the hydroxide from the base to form water. And in acid-base reactions only, it's useful to write water this way, so I can consider these hydrogens and these hydrogens separately. That's a liquid. And the calcium and the chloride are going to pair up. Calcium's a +2 cation, chloride's a -1, so I need 2 of those. So, hydrochloric acid and calcium hydroxide are reacting to form water and calcium chloride. Calcium chloride, is it soluble or insoluble? Well, I get down here to chloride, and rule 3, it's in the generally soluble. There are no exceptions here for calcium, so that's going to be soluble. Okay. So I have my completed equation. Now I have to balance it. 1 hydrogen from the acid, 1 hydrogen in water that came from the acid. 1 chlorine, 2 chlorines, so I need a 2 here. 2 hydrogens in the acid, 1 hydrogen in water from the acid, 2 hydrogens in water from the acid. 2 chlorines, 1 calcium, 2 hydroxides from the base, 2 OHs in water that came from the base. And now it's balanced. So I've done that first step. I've completed and balanced the equation. And now I have the molar ratios 2 to 1 to 2 to 1. Okay, step 2, set up the dimensional analysis. Start with the volume of the base on the left, because that's what's given to us. That's what the amount, the quantity that is given to us, is the amount of this base solution. And we're looking for how many milliliters of the acid solution. So we're going to set that on the far right. That's going to be the goal of this dimensional analysis setup. So here we go. I'm setting up my dimensional analysis. I'm going to start with the volume, the quantity that is being given to me of 45 milliliters of this solution. That's what I'm starting with. And way over here, I'm going to try to give myself as much space as possible. Way over here, I'm going to get to how many milliliters of the acid equals milliliters of the HCl aqueous. And that's my goal. So with that in mind, I would like for you to see if you can go ahead and fill in this dimensional analysis setup. Keeping in mind what I'm saying up here in step 3. Complete the dimensional analysis by converting to moles. We're going to convert that milliliters eventually to moles of the base. And then mole to the acid. And then from moles of the acid to milliliters of the acid solution. And here's a hint for you. The molarity of the solution is just a ratio of its moles of solute to liters of solution. So we're going to treat the molarity as a conversion factor. Now, before we can use molarity as a conversion factor, we have to get into liters, right? So your very first conversion step here is going to be to liters, and then you're going to use the molarity as a conversion step to convert from liters of that to moles of that. Then a mole-to-mole conversion to get to moles of acid. Then the molarity of the acid to get to from moles to liters of acid. And then finally from liters of acid to milliliters of acid. So go ahead and pause the video and see if you can do all that, set that up, and see how that works for you. All right, coming back from pausing the video, I'm going to go ahead and set this up. And I'm going to try to be really parsimonious and careful with my space here, because I've got a lot of conversions that I'm going to have to make. My first step, I know that I eventually have to get into a mole-to-mole conversion. So I'm going to have to get to moles of this base at some point. To get to moles of this base, the only way that I can do that is to use its molarity, to go from liters of the solution to moles of the solution. And the only way I can do that is if I go from milliliters to liters first. So that's going to be my first conversion. I'm going to say it's going to be a conversion, milliliters to liters. And rather than writing all of this out, I'm just going to simplify it to say base, because that's what this is. Milliliters of the base solution to liters of the base solution. Notice that milliliters will now cancel out. And so I've got liters of the base. Now I'm going to use my molarity of the base and convert from liters of the base to moles, MOL, of the base. Notice I'm not abbreviating moles as a capital M, because that's molarity, not moles. It just so happens, though, that the number here will be the molarity number, because that's what molarity is. It's the number of moles per 1 liter, right? So we'll get into the numbers here in just a moment. All right, now that I've canceled out my liters of the base, I've got moles of base. And I'm going to convert to moles of the acid. And there's my mole to mole ratio. That's the heart of my stoichiometry right there. I'm going to have another conversion step. And this is going to be from moles of the acid now, and then in the denominator, to liters of the acid. And again, I'm going to use the molarity for this conversion, the molarity of the acid. And the moles is going to be down here per 1 liter up there. And then barely squeaking it in over here, I've got to convert from liters to milliliters of acid. So liters to milliliters of acid. So there we go. I think everything's barely been able to get squeezed in there. So I think you can see what I'm doing. I'm going to use a different color for the ink for these numbers so that they stand out, since I'm having to squeeze things in a little bit. We know that this is 1,000 milliliters for 1 liter. Same over here. 1 liter is 1,000 milliliters. We know that molarities are the number of moles per 1 liter. So molarity is always per 1 liter, right? So what is the molarity of the base? Well, it's up here. The molarity of the base, 0.10 moles per 1 liter. That's what that means. That right there is 0.10 molar. That means 0.010 moles per 1 liter. Similarly over here, for the molarity of the acid, we were told that it was 0.50. So there we go. This molarity is 0.50 molar. That means 0.50 moles per 1 liter. Okay. And now we have the heart of our stoichiometry, the mole to mole ratio. The moles of the acid, there are 2 moles of acid to 1 mole of the base. Now we have our dimensional analysis set up. We are using our molarities as conversion factors. And because it is a chemical reaction, we're using the stoichiometry approach and not the dilution equation approach. Okay? So we're using the correct technique. So now I'm going to run through this calculation. And I'm just going to calculate everything across on the top and get my answer. And then I'll divide it by the denominators. So 18 milliliters. 2 sig figs, right? 2 sig figs, yes. And there is my answer. So how many milliliters of a 0.50 molar solution of hydrochloric acid would be required to react with or completely neutralize 45 milliliters of a 0.10 molar calcium hydroxide solution, you would need 18 milliliters to do it. Okay? That's how we use molarity as a conversion factor. If we are going from volume to moles, the way we did right here, we went to volume to moles. And then after we do the stoichiometry step of mole to mole ratio, we can go from moles back out to volume. The same way we did right here. We went from moles of acid back out to volume using its molarity. And that's how we do it. So again, this is a stoichiometry problem. It is using molarity as a conversion factor. When do we do this? When we are running a chemical reaction. We do not use the dilution equation for a problem like this. If you used the dilution equation for this problem, you would have gotten the wrong answer. Okay.